You clicked on this video because you saw a model called Needle that can call functions at incredible speeds with only 26 million parameters. You are likely wondering if this is the silver bullet for your next project, a way to run complex AI agents on cheap hardware without breaking the bank. The real stakes here are much higher than just inference speed. If you build your production system on this distilled model, you might save money on compute but end up spending a fortune on debugging, retries, and handling the silent failures that happen when the model gets confused. By the end of this video, you will understand why this extreme optimization creates a false economy that often costs more in engineering time than it saves in cloud bills, and exactly when you should actually run a full-size model instead. Let us start by looking at what Needle actually is. This is a model distilled from the powerful Gemini 3.1 architecture, but stripped down to its absolute bare minimum. It contains only 26 million parameters, which is a tiny fraction of what standard models use. The developers achieved this by removing the multi-layer perceptrons, the complex processing blocks that usually handle deep reasoning. The result is a system that can decode 1,200 tokens per second on consumer hardware. That is blazing fast. On paper, it looks like the perfect solution for running AI on edge devices or low-cost servers. It outperforms larger specialized models like FunctionGemma in single-shot benchmarks. But here is the thing. That speed comes from a fundamental architectural choice that changes everything about how the model understands your requests. Needle treats tool calling purely as a retrieval task. It does not reason about your intent. It scans your prompt, finds the matching function definition, and returns the JSON. This works beautifully when you have a simple, static request like call the weather API for a specific city. The model knows exactly what to do because the path is clear. However, this simplicity is where the trap lies. In the real world, user queries are rarely that clean. People ask questions with ambiguous intent. They use natural language that requires context to interpret correctly. When a user says, "I need to check the status of my order," the system needs to understand what order, what status, and what context the user is referring to. A 26 million parameter model lacks the semantic grounding to make those connections reliably. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Because the model cannot reason through ambiguity, it often guesses. It might hallucinate an argument or pick the wrong function entirely. When this happens in a development environment, you catch it immediately. You see the error, you fix the prompt, and you move on. But in a production system, things get messy. You might get a response that looks syntactically correct but is semantically wrong. The model returns a valid JSON object, but the data inside is incorrect. Your downstream services accept this data and try to process it. Suddenly, you have a system that is failing silently or executing the wrong actions. The cost savings from running a tiny model are instantly negated by the operational overhead of handling these failures. Now consider the complexity of modern automation. Most production systems do not rely on a single, isolated function call. They require multi-turn conversations where the user refines their request over several exchanges. They need to handle parallel tool calls where multiple actions must happen at once. Needle struggles significantly with these scenarios. It lacks the emergent ability to track context across turns or to coordinate multiple actions simultaneously. This forces engineering teams to build brittle, custom validation layers on top of the model. You have to write code that constantly checks if the model's output makes sense, and if it does not, you have to retry or fall back to a different strategy. This is what I call the reliability tax. Every time you choose the smallest possible model to save on inference costs, you are paying a tax in the form of increased engineering complexity. You are trading a predictable compute bill for an unpredictable maintenance burden. The marginal reduction in cloud spend is often tiny compared to the hours your team spends debugging, why the agent called the wrong API, or why it forgot the user's previous instruction. The evidence from early adopters shows that while Needle is superior for deterministic static use cases, it fails to generalize the robustness of full-sized models when tool definitions are complex or user queries are unclear. Here is the critical insight you need to take away. The decision to use a distilled model is not just a technical choice about parameters. It is a strategic choice about where you place the burden of intelligence. When you use a 26 million parameter model, you are pushing the burden of intelligence onto your application logic. You are asking your code to do the reasoning that the model should be doing. This creates a system that is fragile. It works perfectly until the edge case arrives, and then it breaks in ways that are difficult to predict. In contrast, a full-size model has the internal capacity to handle ambiguity, correct its own mistakes, and understand the nuance of human language. The last mile of function calling is often the most expensive part of the pipeline. It is the gap between what the user wants and what the code executes. Larger models bridge this gap because they have enough parameters to understand the semantic weight of your request. They can infer that when you say, "check my account," you mean, "look up your balance, not your transaction history." Needle cannot make that inference reliably. It treats every request as a lookup task. This means that for general-purpose automation, the risk of hallucination and context collapse likely outweighs the marginal inference speed gains. The most pragmatic choice for reliability is often to run a full model, even if it costs a bit more to run. For teams optimizing for the smallest model possible, there is a real risk of creating brittle systems that require constant manual intervention. The long-term return on investment often favors adopting full models for tool calling. This approach reduces the complexity of the surrounding orchestration code and allows your team to focus on building features rather than patching holes in the agent's logic. The speed of a 26 million parameter model is tempting, but it is a false economy when it forces you to build a house of cards around it. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.